Every major machine learning model explained in 25 minutes. In this video, I'll be doing a high-level overview of each of these machine learning models, since if I went into detail for each one, this video would be very, very long. Literally every single one of these models can have an entire video dedicated to them. In fact, I'll probably do that sometime down the line. If there's a specific model you want me to cover in the future, just put it in the comments below. I give you anywhere from 0 to 100% of my word that I'll cover it. First off, if you hear the words machine learning and think to yourself, "What the hell is even that?" Then here's a simple definition. Machine learning is basically giving computers a bunch of data and letting them slowly figure things out instead of hard coding every tiny instruction. All machine learning can be split into two categories: supervised learning and unsupervised learning. Supervised learning is when the model is trained on labeled data, meaning for every input, there's already a correct answer provided. For example, imagine showing a child thousands of pictures of cats and dogs, each one labeled with what it is. Over time, the child learns to tell them apart on their own. Supervised learning works the same way. You feed the model thousands of labeled examples, and it learns the patterns that connect the inputs to the correct answers. The model learns by comparing its predictions to those correct answers and adjusting itself until it gets better. Think of it like studying with an answer key. You already know what the right answers are, and you keep practicing until you can get them right on your own. Within supervised learning, there are two main types of tasks. The first is regression, where the goal is to predict a continuous numerical value. Continuous just means the output can be any number along a range, not just a fixed set of options. Think of things like predicting a house price, forecasting tomorrow's temperature, or estimating someone's salary. The second is classification, where the goal is to predict a discrete category. Discrete means the output is one of a fixed set of options. There's no in between. Either the email is spam or it isn't. Either a tumor is malignant or it's benign. Either the image is a cat, a dog, you get the idea. Now, not all data comes with labels. Sometimes you just have a massive pile of raw data and no idea what's inside of it. No answer key, no guidance, nothing. That's where unsupervised learning comes in. Instead of learning from labeled examples, the model looks at all the data that has no labels and has to figure out the patterns and structure on its own. For example, imagine dumping 1 million customer transactions into a model with no instructions. Unsupervised learning can look at that data and automatically discover that there are distinct groups of customers: big spenders, occasional browsers, and discount hunters. Nobody told it those groups existed, it found them on its own. We'll get into that later. The simplest regression model is called linear regression. The idea is straightforward. Think of it like drawing the best fitting straight line through a scatter plot of data points. The goal is simple: predict an output y, called a dependent variable, based on an input x, called the independent variable. For example, let's say we want to predict a student's exam score based on how many hours they studied. Every student in our dataset becomes a dot on a graph: hours studied on the x-axis, exam score on the y-axis. Linear regression draws the best fitting line through all of those dots. So if a new student studied for 6 hours and we wanted to predict their score, trace up from 6, hit the line, and read across. That's our prediction. The equation looks like this. Y hat is the predicted output, beta 0 is the intercept where the line crosses the y-axis. Beta 1 is the slope, how much y changes for every unit increase in x, and x is the input feature. In reality, one variable rarely tells the whole story, which leads to multiple linear regression, with its bigger, more intimidating looking older brother equation. Each x represents a different independent variable: hours studied, hours slept, assignments completed, and so on. Each corresponding beta coefficient tells you how much that specific feature contributes to the prediction. Linear regression is best used when you need to predict a continuous numerical value and there's a clear relationship between your inputs and your output. Next up is logistic regression, and despite the name, it's not actually used to predict continuous values like linear regression. Instead, it's used for classification, meaning the output is a category, not a number. The most common case is binary classification, where the answer is one of two things: yes or no, true or false, 0 or 1. For example, we might want to predict whether a patient has a disease or not. based on their age, blood pressure, and cholesterol levels. The model simply outputs a yes or a no. The core idea is this. Logistic regression takes the same linear regression equation we already know, but instead of outputting a raw number, it passes it through something called a sigmoid function, which produces an S-shaped curve, which looks like this. The function squishes the output into a value between 0 and 1, which we interpret as a probability. So if the model outputs 0.85, that means it's 85% confident that the patient has the disease. Then we apply a cutoff, usually 0.5. If it's above 0.5, it's a yes, and if it's below 0.5, then it's a no. Logistic regression is best used when you need to classify something into one of two categories and the relationship between your inputs and outputs is relatively straightforward. Naive Bayes is a classification algorithm built on two different parts. The Bayes part comes from Bayes' theorem, a mathematical formula for updating your belief about something based on new evidence. The naive part comes from a bold assumption the algorithm makes, that all input features are completely independent of each other, meaning one feature has absolutely no influence on another. Take spam detection as an example. When naive Bayes looks at an email, it scans each word independently and asks, given that this email is spam, how likely is it to contain this word? It does this for every single word, multiplies the probabilities together, and compares the result for spam versus not spam. Whichever comes out higher wins. The key formula behind this is Bayes' theorem. What Bayes' theorem is really saying is take what you already believed, update it based on new evidence, and you get a smarter, more informed probability. That's it. Naive Bayes is best used when you need a fast, lightweight classifier, especially on text data. If your data is text-heavy and you need something reliable without a lot of computational overhead, Naive Bayes is a solid pick. Our next model is K-nearest neighbors, or KNN for short. The core idea of it is simple. To predict what something is, take a look at what's around it. In K-nearest neighbors, you classify a new data point by looking at the K closest points in your training data and take a majority vote. Imagine you walk into a party and you have no idea what kind of party it is. Instead of asking the host, you just look at the people standing closest to you. If the three nearest people are all talking excitedly about Python, you're probably at a tech meetup. If they're all holding guitars and wearing vintage band t-shirts, you're at a music event. You didn't need to survey the entire room, you just looked at your nearest neighbors and made a call. KNN does the exact same thing. The K in KNN is just a number that you choose. For instance, if K is equal to 3, it'll look at the 3 closest data points. If K is 5, it looks at the 5 closest. Once it finds those neighbors, it does one of two things depending on the task. First is classification. This means it takes a majority vote. Whatever class most of the neighbors belong to, that's the prediction. The other is regression. Here it takes the average of the neighbors' values as the prediction. So how does KNN figure out who its nearest neighbors are? Typically it uses something called Euclidean distance, which is just a fancy way of saying the straight line distance between 2 points. As a rule of thumb, if your dataset is small and the relationships between data points are based on similarity, KNN is a solid choice. Support vector machines, or SVM for short, is a classification algorithm that works by finding the best possible boundary, called a hyperplane, that separates two classes of data. The goal is not just to find any boundary that separates the data, but the one with the maximum margin, which is the distance between the boundary and the nearest data points from each class. To understand this visually, imagine two groups of dots on a graph, red dots and blue dots. There are many possible lines you could draw to separate them, but support vector machines finds the one that is furthest away from the closest dots on both sides. Those closest dots are called support vectors. They're the data points that are literally holding up the boundary. Support vector machines' entire goal is to maximize the margin. Now here's where it gets interesting. What if the data isn't separable by a straight line? Support vector machines solve this by using something called a kernel trick, which basically transforms the data into a higher dimension where it suddenly does become separable. You can think of it like lifting dots off a flat table into 3D space, so a flat plane can now separate them perfectly. That's what allows support vector machines to handle more complex, nonlinear data. That's badass. Support vector machines works best when you have a clear margin of separation between classes and when working with high-dimensional data, such as text classification or image recognition. We're now going to transition into trees.
What?
No, not those trees.
Wrong.
I'm talking about decision trees. A decision tree is exactly what it sounds like. A tree-like structure of decisions that leads to a prediction. It's literally a tree of yes or no questions. It works by repeatedly splitting the data into smaller and smaller groups based on the most informative feature at each step until it reaches a final answer. Each step narrows down the possibilities until you arrive at the answer. For example, imagine you're trying to predict whether someone will buy a product. The tree might start by asking, is the person over 30? If yes, then it goes down one branch. If no, it goes down another. Then it asks another question and another until it reaches a final prediction, buy or don't buy. Each point where the tree makes a decision is called a node. The very first node at the top is called the root node. It's the most important split in the entire tree. The final nodes at the bottom, where the predictions live, are called leaf nodes. Decision trees are most useful when you need a model that is easy to interpret and explain. You can literally follow the branches and see exactly how the prediction was made. For example, a bank might use a decision tree to predict whether a loan applicant should be approved, starting with questions like income level, credit score, and employment status, each split narrowing down the risk profile until a final decision is reached. Next is random forests. A random forest is essentially a team of decision trees, and as the name suggests, a whole forest of them. The idea is simple. Instead of relying on one decision tree to make a prediction, why not build hundreds of them and let them vote? Here's how it works. Random forest builds a large number of decision trees, but with two key twists. Number one is random data sampling. Each tree is trained on a random subset of the training data, rather than the full dataset. This means each tree sees a slightly different version of the data and learns slightly different patterns. Number two is random feature selection. At each split, instead of considering all features, each tree only considers a random subset of the features. This forces diversity across the trees, which helps cancel out the mistakes of the other decision trees. This approach of combining multiple models together is called ensemble learning, and it's what makes random forest so powerful. Next up is XGBoost. Aside from sounding like it belongs in a Fast and Furious movie,
I said forget about it, cuz.
XGBoost, which stands for Extreme Gradient Boosting, is a powerful machine learning algorithm where each tree is designed to learn from the mistakes from the previous one. Instead of building trees independently like random forest, XGBoost builds them sequentially. The core idea behind XGBoost is a technique called boosting. The sequential nature allows each tree to focus on the errors that the previous tree got wrong. The gradient part of the name refers to how XGBoost measures and corrects those errors. It uses a mathematical technique called gradient descent to minimize a loss function, which is just a measure of how wrong the model's predictions are. Each new tree is built in the direction that reduces the error the most. XGBoost is best used when you need maximum predictive performance on structured tabular data. Now let's get into neural networks. If there's one topic in this entire video that has fundamentally changed the world, it's this one. Neural networks are the engine behind modern AI. Deep learning, large language models like ChatGPT, image generation, self-driving cars, all of it traces back to neural networks. Loosely inspired by the human brain, a neural network is made up of layers of interconnected nodes, similar to our brain's neurons. There are three types of layers: an input layer, hidden layers, and the output layer. The input layer is where the data enters the network. Each node in this layer represents one feature, such as age, income, or pixel value. The hidden layers are the layers in between, where the actual learning happens. Here, the network learns to detect patterns and relationships in the data by adjusting the connections between the nodes. Then lastly, the output layer. This is where the final prediction comes out. The connections between neurons each have a weight, a number that determines how much influence one node has on the next. During training, the network adjusts these weights to minimize its errors, gradually getting better at making predictions. Neural networks are best used when your data is complex and high-dimensional, such as images, audio, or text, where traditional algorithms struggle to find patterns on their own. Next up is a specific type of neural network called a convolutional neural network, or in short, CNN. And no, I don't mean the news channel. The CNN I'm talking about is actually good at telling you what to pay attention to. Anyways, CNNs are designed specifically for processing data that has a grid-like structure, most commonly images. While a regular neural network treats every input feature equally and independently, a CNN is smart enough to understand that in an image, nearby pixels are related to each other and should be looked at together. The core idea behind a CNN is the convolution operation. Instead of looking at the entire image all at once, the network slides a small filter across the image, scanning it piece by piece and detecting patterns like edges, shapes, and textures. In the early layers, the network picks up simple patterns like edges and corners. In the deeper layers, it starts combining those simple patterns into more complex ones, like eyes, ears, and eventually entire faces. It's like going from recognizing individual letters, to words, to full sentences. CNNs are best used when your data has spatial structure, meaning the position and relationship of features matter. They are the go-to choice for image recognition, video analysis, and medical imaging. If neural networks are the engine of modern AI, then transformers are the turbo boost. Now when I say transformers and you think of this, then all I have to say is,
stop it. Get some help.
And allow me to clarify. Transformers are a type of AI architecture that can read and understand entire sentences at once, rather than one word at a time. It completely changed the way machines process and understand language. ChatGPT, Google Gemini, and virtually every modern large language model you've heard of is built on this architecture. Before transformers, models processed data sequentially, one word at a time in order. This made it slow and difficult to understand long-range relationships in text. For example, in the sentence, "the trophy didn't fit in the suitcase because it was too big," well, what does the word "it" refer to? While humans figured this out instantly, older AI models struggled because they processed words one by one and lost context along the way. Transformers solved this with a mechanism called attention, specifically self-attention. Instead of processing words one at a time, the transformer looks at the entire sequence at once and figures out which words are most relevant to each other. This ability to understand context across an entire sequence is what makes transformers so powerful. Next up are generative adversarial networks, or GANs. These are one of the most creative ideas in machine learning. Instead of predicting a label or classifying an input, GANs are designed to generate entirely new data, images, audio, video, or text. The way they do this is through a two-player game between two neural networks that are essentially trying to outsmart each other. The first is called the generator. Its job is to create fake data that looks as realistic as possible. The second is called the discriminator. Its job is to look at data and decide whether it's real or fake. The two networks are trained simultaneously in direct competition with each other. Think of it like an art forger and an art detective. The forger keeps producing fake paintings, trying to fool the detective. The detective keeps getting better at spotting fakes. So the forger has to get better too. Back and forth, round after round, until the forger is so good that even the detective can't tell the difference anymore. That's exactly how GAN trains. GANs are best used when the goal is to generate new, realistic data rather than classify or predict existing data. They're behind some of the most impressive AI applications you've seen: deepfakes, AI-generated art, synthetic data generation, and photorealistic image synthesis. Impressive, slightly unsettling, and maybe a little bit illegal in the wrong hands. Next up is K-means clustering, which is an unsupervised learning algorithm. That means there's no labels, no right answers, and no one telling the model what to look for, like I explained earlier. Instead, K-means is given a dataset and tasked with finding natural groups, or clusters, within the data entirely on its own. You tell the algorithm how many clusters you want, that's the K, and it figures out the best way to divide the data into that many groups. Each group is defined by a centroid, which is just the center point of that cluster. The algorithm assigns every data point to the nearest centroid. Then it recalculates the centroids based on the new assignments, and repeats this process until the clusters stop changing. K-means is best used when you want to discover natural groupings in unlabeled data. It's widely used in customer segmentation. For example, a retail company might use K-means clustering to group customers into clusters based on purchasing behavior, allowing them to tailor marketing strategies to each group. PCA, or Principal Component Analysis, is another unsupervised learning technique, but unlike K-means, which finds groups, PCA is about dimensionality reduction. In plain English, that means taking a dataset with lots of features and compressing it down into fewer features, while still keeping as much of the important information as possible. To understand why this matters, imagine you have a dataset with 100 features. Not all of those features are equally useful. Some are redundant and barely relevant, and feeding all 100 into a model is inefficient and can actually hurt performance. PCA solves this by finding the directions in the data where the most variation exists, called principal components, and projecting the data onto those directions, effectively summarizing the most important information in fewer dimensions. Under the hood, PCA computes something called the covariance matrix. This matrix helps figure out which directions in the data have the most variation and projects the data onto those directions. It's kind of like taking the perfect selfie. You find the best angle with the best lighting that captures you in all your beautiful glory. PCA is best used when you have high-dimensional data and need to reduce complexity before feeding it into another model, or when you want to visualize high-dimensional data in 2D or 3D. It's widely used in things like image compression. If your data has too many features and your model is struggling, PCA is often the first tool to reach for. Lastly, we have reinforcement learning. Reinforcement learning is all about learning through trial and error. The core idea is built around three things: an agent, an environment, and a reward. The agent is the learner, the thing that's making decisions. The environment is everything the agent interacts with. And the reward is the feedback signal, a score the agent receives after taking an action, telling it whether that action was good or bad. The agent's goal is simple: maximize its total reward over time. It's kind of like training a dog. Every time the dog does something right, you give it a treat. Every time it does something wrong, no treat. Over time, the dog figures out exactly what behavior gets the most treats. Reinforcement learning works the same way. What makes reinforcement learning powerful is that the agent doesn't need to be told what the right answer is. It discovers it on its own through exploration and feedback. Over thousands or even millions of iterations, it learns a policy, which is a strategy for deciding what action to take in any given situation to maximize its reward. Reinforcement learning is increasingly being used in robotics and autonomous vehicles, and if you've ever been amazed by what modern AI can do, there's a good chance reinforcement learning had something to do with it. Now, before we continue, quick question. Have you ever noticed that learning machine learning hands-on is weirdly frustrating? Everything's either too theoretical, too confusing, or so boring it feels like homework. That's actually the exact reason I built my newsletter, to fix that problem and make machine learning not just easier, but fun. If you really want to go deep and actually practice machine learning hands-on, I just launched the Gradient Descent Pro tier. This is where you don't just learn, but apply through practice. Every week you get a hands-on coding environment where you're actively implementing machine learning concepts yourself, complete with visual demos, step-by-step explanations, real-world tasks, hints, and full solutions. And that's just the coding side. You also get weekly quizzes at 3 difficulty levels, easy, medium, and hard, that don't just tell you you're wrong, but explains why. And every week you get a beautifully illustrated visual cheat sheet packed with Python snippets and key concepts, the kind of thing you'll actually want to keep open while coding. And on top of all that, you also get a completely free machine learning ebook. It covers the fundamentals, the different types of machine learning, the algorithms you'll actually use, and the math behind it all in an easy to understand, digestible format. All of this is normally $9.99 a month, but the first 100 subscribers get the founding members deal, everything locked in permanently for $5 a month. That's basically one latte. Once those spots are gone, they're gone. So don't sleep on it, the link's in the description. And congratulations, that's every major machine learning model that you need to know. And remember, this was just a high-level overview. If you want a deep dive into any particular model, drop it in the comments below and I'll make it happen. If you guys found this helpful, go ahead and subscribe because there's a lot more where this came from. Thank you guys for watching, and I'll see you in the next video.